Hello, everyone. Welcome back. It's been roughly 3 minutes and several roasts later in the room. We have a good time here. If you guys are ever in the Dallas-Fort Worth area for vacation, I think this is actually a great vacation spot. This specific room on this day during these hours. You're like pulling your hair out. You're like, absolutely not. Why do you always look like you're suffering? Listen. If anything, it's my fault. The thing is, I don't care. I do not care about your suffering. I care about you doing well in the MCAT. And almost nothing else. Chapter 9 is what? Solutions. Not solutions to your problems, unfortunately, but solutions where you dissolve something in something else. A solution is a solute plus a solvent. The solute is the thing you are dissolving. And the solvent is the thing that you dissolve into. I have sugar. I put it in water. I dissolve. The sugar is the solute and the water is the solvent. So solvation is actually the method by which molecules of the solvent surround molecules of the solute and pull them away from one another and suspend them within solution. For example, if you have something like sodium chloride dissolving inside of water, they will start like this. You put them in the water, and it will look like this. Why? Because the dipole, the nature of the dipole of water is that the oxygen has a negative dipole. It surrounds that sodium molecule and dissolves it. The same thing for the chloride, if you can imagine, or I guess I'll just do it myself. Because then someone's going to be like, I can't imagine, and then I'll be like, oh my God. I'll start crying, and I'll go home and write a letter about how sad I am. It's a very common occurrence. The positive dipole, the positive end of that dipole is localized between the hydrogens, right? Because remember, if we're looking at the specific dipole and the physics of it, physics, right? We have a pull that way, a pull that way. The overall dipole would be an addition of those two. The left and right components of those vectors will cancel out, giving you an upward component of the dipole. The negative end being here, and the positive end being here, between the two hydrogens. Does that make sense? Right. So that's why you have this dissolution like this. The same thing happens with something like a glucose molecule, where the oxygens are going to be partially negative, the carbons are going to be a little bit positive because of the pull from the oxygens, things like that. So the water is going to arrange itself around the glucose in an interesting fashion. Also, you have the hydrogen bonding on top of that. So that's very interesting. But what we want to get down is that the dissolution, the idea of solvation, is where the molecules of the solvent actually surround the solute, and you get suspension inside of that solution. Right. Now we can have, real quick, the entropy of the system does what when you dissolve? In water specifically. The entropy of the water has actually gone down because now they're more organized. They're put into an organized fashion. That means that for solvation to be spontaneous, you need it to be an enthalpic process, not an entropic process. This is a lot like the protein discussion we had before. There are some things that are very soluble. There are some things that are not so soluble. There are some things that are not soluble at all, right? And this is known as solubility. And every single sort of molecule that you can dissolve inside of something has a level of solubility that you can get up to and not exceed. You can be undersaturated, saturated, and hypersaturated, right? So undersaturated means you've dissolved a little bit and you can still dissolve more. Saturated means you've dissolved just enough for that to be completely full and the solvent cannot hold any more solute molecules. And hypersaturated is you boiled the thing, dissolved a bunch into it, cooled it back down, and kept it still enough so that the solvent doesn't, the solute doesn't crash back out into solution. And yes, it's called crashing out. That's literally called, like that's what it's called when something comes out of solution like that. You guys know that little experiment that I tell you to reference all the time? It's like the silver chloride experiment. And you put the NaCl and you see that white liquid that it like falls out of the vessel. It's like a cloud. That's called crashing out the silver, right? That being said, the solution inside of water has a very specific name. And also, we can talk about the method by which things dissolve and how they do so. So if we have a metal oxide, M2O, right? And we were to put this inside of water, and we say 2M plus O2 minus, metal and its oxide, right? We can call these aqueous, because that is what it looks like inside of a solution. And we can write a K expression, which is remember, the products over the reactions. This is the K of solubility. It's KSP, the solubility product. It's called a product because we're going to multiply the things that are in the products, correct? So we have M squared O2 minus. Yes? Let's get rid of it. Whatever. Just forget it. They're hardly ever going to give you that anyways. Perfectionism. Am I going to put this over MO? Why not? Solid things don't have activity in the solution. The only things that are active within the solution are things that are solubilized within the solution itself. So solids don't have activity, which means this is your KSP. This looks oddly like another thing we saw before that we're much more familiar and much more comfortable with. I'm going to draw this over and over again, especially in organic chemistry. You're going to see me go through this so many times. Ka. Ka is KSP of an acid. That's what it is. And that makes sense because when we talk about acids and their different strengths, you are actually talking about what? The ability for the acid to dissolve inside of the water. It just so happens that the acid is a liquid in and of itself, so it goes inside of that KSP. That is now called Ka. And this is the same thing as saying HA plus H2O yields H3O plus A minus, the conjugate base of the acid. Does that make sense? You guys understanding that? Did I lose any of you? We have a second person who looks like they're suffering. Vishal's always happy to be here. That's my guy. Give me some, man. I wish you guys could see the room from my perspective sometimes. Because you'll look around, there's like some people watching football, right? There's some people who are like viciously, violently taking notes, like they're taking the exam tomorrow. There's some people who are legitimately tearing their hair out every 5 minutes. And then there's some people who I can't read their face at all. They could be having the worst day of their life, or they could be like jumping over the moon for joy, and I would have no idea. Babe, one thing that they talk about here is the concept of chelation. And chelation comes up quite a bit, not in the questions in and of themselves, but within the passages. Chelation is basically the ability for a molecule to bind into the d orbital of a transition metal. That is chelation. It's almost like forming coordinate covalent bonds, right? That's normally where you're going to see chelation. And you can actually see a little diagram right here of chelation. That's from the textbook. It says chelation of iron with 2 molecules of deferracerox. I'm not that great at biochemical pharmacology, but I believe that is an iron chelating agent that we use for hemochromatosis and iron poisoning. Deferracerox. Because like this D-ferra minus iron, right? That whole prefix is for, removal of iron. Someone's reaching for an iron pill right now.
Does it bother you?
No, not at all. It's just funny that we're talking about iron, and it reminded someone to take their iron pill. Do they work? People who have anemia and like actually take iron pills, do they like work if you take them properly? I've heard mixed things, but also I've heard mixed things from people who are like, oh, I take it sometimes I don't. Like if you want it to work, you have to take it every single day.
I've been all of those people. When I'm like consistent, it makes a huge, especially in the winter. Like I can feel
Yeah.
the difference in my bones.
Yeah, because you get like that bone pain sometimes when you have like when it gets really
When
cold.
it's really cold, and it just like
Yeah.
it hurts my bones.
Yeah. Anemia is tough. Anemia is very, very tough. It's very tough medically. Medically, it's very complicated. Because you'll get there. You guys will get there.
I like the fish.
You like the fish?
Like literally a block of iron you cook into your food.
Oh, yeah.
That way you can just eat your normal meals.
I've heard of that before, like cooking iron, like cooking with a cast iron pot, and then also cooking with like an iron block that seeps into your food, especially like for more acidic foods like pasta sauces and things like that. My only concern there is like, are you able to regulate the amount of iron intake that you get per day? Like, are you able to know that you're getting a proper amount?
I think it's just you've increased the iron in your food. I don't think it's a specific amount.
Because iron metabolism is actually quite interesting as well. There's no real way for your body to get rid of iron once it's in the body. There's a way to block it from entering, but there's no real way for you to get rid of iron, which is why when you have a deficiency in the protein that blocks iron from entering, you can get iron overload, which is called hemochromatosis. Yeah, you could do that, I mean. They talk a little bit about like concentrations and things like that. Talk about molarity. We've talked about molarity before. Talked about normality before. They talk about dilutions. Guys, M1V1 equals M2V2. That's dilutions. You have a molarity, you want a molarity, you have a volume, you want... So exciting! I can't wait to start biochem, dude. This is just, like, because you see how I'm, like, wiping the board every 30 seconds, like, different topic. Biochem is just one beautiful line of a story. And then you erase the whole board, and then it's like another line of a story, and you erase the whole thing. Like one lecture in biochem will probably take us this whole thing. Like we're gonna have to move around the camera a little bit and like probably push the camera back.
You could even use the sciences like.
We could. It's so beautiful. Yeah. So we did solubility, product constants, blah blah blah. Do you guys want to go over the common ion effect again? Yeah. It's important to solutions, things like that. Who knows what the common ion effect is? Anyone? Anyone confident in their knowledge of the common ion effect? Michelle, we've been over this together. You want to help me out?
No, I'm not confident.
Okay. Let's do it. The common ion effect is rooted in the idea of Le Chatelier's principle. What's the common ion effect?
So if you were to add a
Give me a proper example that I can put on the board.
like AgNO3,
Okay.
if you had that also in your chemical reaction, Ag+.
But like, how am I going to set this up? So when you're setting up a question or an example for yourself for your notes, take something that you know very well. What do we know very well? This. That we know very well. Yes?
Ice charts.
Huh?
Ice charts.
Ice charts, we could do that. We'll do that eventually. It's on my list of things to do.
You told us to set a reminder before like.
Oh, right. For this?
That's right now.
Yeah. Oh, yeah. That is right now. Wow. Okay, we'll do ice charts. So this is our little equation right here. Oh, I really don't want to do ice charts. Okay, and if, for the sake of your sanity, I'll also write this out in this manner. Now, this already exists in an equilibrium. Guys, by the way, not two different things. These are the same thing. These two are the same thing. Count the carbons, I dare you. Okay. These two are the same thing, and for the sake of the lesson, we're going to say that this is already an equilibrium within its own vessel, correct? Of water. Within that vessel of water, I am going to dump 5 grams of sodium acetate, right? That is going to dissolve into we now find a common ion. This is known as the common ion effect. And when you add that common ion, it elevates the concentration of that ion within all of its equilibria. But that sodium acetate is actually fully soluble inside of water. That's not an equilibrium, that's a full dissolution. That's dissolving 100%. So we don't have equilibrium here, but we do have equilibrium here. So by elevating the level of the acetate, we are actually, by Le Chatelier's principle, going to be pushing back towards the reactants, correct? This elevation will push back towards the reactants and increase the level of the acid that we have. I don't know if you guys can see my handprints from when I slap on the board. You know, it's so funny. Back in my old basement back home, where I filmed my first videos ever. If you guys are ever in New York, I'll definitely, for the guys, I'll definitely introduce you guys to my parents, whatever, you guys can come over for dinner or whatever it is, right? I'll take you to where I used to record my old lectures, like the OG ones, the ones that aren't even on YouTube anymore, right? That's where I recorded my first ever TikToks. You got the whiteboard, and then right next to the whiteboard is the wall. And on the wall, you'll actually see all of these little marker stains. So what happened, I would erase, and I'd lean on the wall like this while teaching. And then all the marker would end up on the white wall. And you can still see them there. And I left them there. I don't want to paint over them because it's a testament to how far the journey has gone. That was 5 years ago now that I started teaching in my basement. Le Chatelier's principle says that by the elevation of this equilibrially, I don't know, this active molecule within the equilibrium, we have to push back. And that's going to increase the concentration of the dissolved acid or the undissolved acid within its own equilibrium. This actually, on the MCAT, is shown as a decrease in the percent dissolution / solubilization. They like the letter ionization, the percent ionization of the acid. So my question to you is, what happens to the pH? I had an initial pH. I added sodium acetate. By adding the sodium acetate, I threw off the equilibrium and pushed it back towards the reactants. What's going to happen to the pH? The pH is going to go up because we're taking away H3O plus along with the acetate. So by the drop in the H3O plus, the negative log of H3O plus, if we were to drop this becomes more negative. That negative means it's going to go up. The pH increases, and this becomes more basic because of the decrease of the percent ionization of the acid in the first place through the common ion effect. Any questions about that?
You added an acid.
I will slap you. No, I'm kidding. If I added what?
You added an acid.
I added the conjugate base of the acid.
Oh, okay, got it. Sorry. Never mind.
What would happen if I did add the acid? A similar thing would actually happen. If I added pure hydrochloric acid into here, it actually just combined with the water to make H3O plus. That bump would send it back. The percent ionization of this acid would go down, but the pH you'd actually have to calculate because now you've added acid into the container. And it would depend on the molarity of the hydrochloric acid that you put in. It could be 0.00001 molar. It would still affect the equilibrium, but would it have any effect on the pH? Maybe not. But if you put 5 molar HCl into the flask, now you have a problem with the pH. And it really depends on the volume of the hydrochloric acid that you put in, along with the volume of the actual solution. Does that make sense?
Yeah.
We've talked extensively about osmotic pressure. PC, PI, pi C, pi I. Right? What is the M? The molarity, correct? Sorry, capital M. Not meters, but molarity. The RT is the constant that they're probably going to give you on the exam. And the I is the what? The number of moles of what? The number of moles of actual solute that you get within the solvent solution. So from glucose, you get 1. From magnesium chloride, you get 3. MgCl2. Because 1 mole of magnesium and 2 moles of chloride ions. This is known as the Van't Hoff factor. I think it's spelled like Van't Hoff. That is for the the osmotic pressure. There is a difference between oncotic and osmotic pressure. I just don't know it off the top of my head. Ice charts. For this equilibrium, the Ka is equal to 1.8 times 10 to the negative fifth, and the Ka is equal symbolically to I'm being very serious. You guys should get into the habit of drawing out organic molecules, because when we get to orgo, you're going to have to breeze through the molecules with me, or else every lecture is going to take much longer than it should. I draw organic molecules very fast. Granted, I'll give you a little bit of time, but just get used to putting them into your brain. Because eventually, if I draw something like this, I don't want to have to wait for you to catch up. The chart here, Am I still on frame over here? Okay. Remember, scientific equation, scientific notation. Is anyone still choppy on scientific notation, or did we pretty much cover that within our mathematics lesson? I'm going to upload it soon. I've just been waiting. I'm also waiting for winter break to upload that CARS webinar, because I think a lot more people will watch it if I put it out during that time. That's when people really start to practice and things like that. Are you guys enjoying having a good time? Chemistry is more fun than biology, right? No? You don't like it? You guys are lame. You guys are boring and lame, and your opinion doesn't matter. Oh, there you go. Speaking of boring and lame. Everyone here gets roasted out of my love for them. If you have not gotten roasted by the end of the year, you're a disappointment.
You weren't worth roasting.
Huh?
You weren't worth
You weren't worth roasting. Don't pass out in my lecture hall because you didn't take your iron pill, okay? That's what everyone says. That's what they all say. Just like me when I said I didn't need antidepressants. All right. Ice charts literally follow this paradigm, ICE. Initial, change, and equilibrium. The equilibrium is literally, I want you to put a line right here. What does this do? it allows you to understand the way that things change over time, right? The initial is usually going to be given to you. They say within 500 milliliters of water, I place 2 moles of acetic acid. Everything that goes down here needs to be in molarity. Everything. So what is that in molarity? What's the molarity of the acetic acid? It's very dry in here. I feel my lips cracking. What's the molarity of the acetic acid? How do you calculate molarity? Moles over liters. How many liters is that? 0.5. 2 divided by 0.5 is 4. You go 4 molar. That's all the information you need. This and that. The change is minus x. You're saying that a certain amount of that is going to disappear and dissolute into the other side. However much dissolutes, that's the loss that you have in the equilibrium position, correct? You guys remember this from like 10th grade chemistry, 11th grade chemistry, yeah? And this is traumatizing for me. I hate this stuff. Then, in the beginning, you obviously have 0 because you haven't started with anything. And here you have plus x and plus x. If you had cofactors here, you could be plus 2x, plus 6x, plus 3x, whatever it is, whatever the cofactor is. So here you have x and x. If you wanted to figure out the molarity of those, you could. And here I'm just going to do this, because water doesn't have activity in the solution. And I'm going to set it up like this, that 1.8 times 10 to the negative 5th is equal to x times x over 4 minus x. Here's a catch. When the Ka is in the realm of less than 5 times 10 to the negative 5, the subtraction becomes irrelevant. It's basically over 4, basically, because we're just solving for that. So the concentrate, so little of this is dissolving, it's basically 4. Basically still 4 and just a little bit less. How much less? This is going to be 1.8 times 10 to the negative 5th equals x squared over 4. X squared is equal to 4 times 1.8 times 10 to the negative 5th. I'm going to do something here. X squared equals 18 times 10 to the negative 6th times 4. What's 18 times 4? 32, 72, right? X squared equals 72 times 10 to the negative 6th. Take a square root. X equals radical 72 times 10 to the negative 6th. This whole thing is x equals 72 times 10 to the negative 6th to the 1/2. Right? What's that going to come out to? How do we do this? How do you do that math? Take the square root of 72, and then what's the 10? What do you do with the 10 to the negative 6th? Divide by 2. So it's going to be whatever this is times 10 to the negative 3rd. What's the closest thing you can think of to 72 that is a perfect square? Huh? 8 is going to be 64, and then 9 is going to be 81. So somewhere between 8 and 9, right? Let's say 8.5. Someone actually do that in there. Hey, 8.48, 8.5. It's almost like this guy's taught this before. So then we know that this is going to be 8.5 times 10 to the negative 3rd and 8.5 times 10 to the negative 3rd. And if you really wanted, you could say 4 minus 8.5. You know what? Just to be petty. There you go. Just for completion's sake. 3.9915. And that goes to show how weak acids really are. Look at how little of that dissolved. Right? Here's the thing. That's how you do a simple ice chart. Makes sense, right? Makes sense. That's in 500 mils. In 500 mils, I'm going to take, you remember the common ion effect question? I'm going to take 5 grams of NaC2 H3O2 and place it inside of this flask. So now, what I need to do is this. Everyone stop writing. I don't want you to write this. I just want you to observe the mathematics and how we're going to do this. Someone with a periodic table, tell me the gram formula mass of sodium, or the atomic weight of sodium. 28? 22. We have 22, huh? 22 point what? Huh? 23. 23, 24, 3, and 32. Sorry. 3 and 32 is 35. 23 and 35 is 58. 58 and 24 is 78, 82. Correct? Did I get that wrong? 35. 35 is going to be
No, because you have 47 plus 350, 82,
82. Yeah. 82 grams per mole. This is how we're going to do this. 5 grams multiplied by 1 mole over 82 grams per mole is going to be 5 over 82 grams per mole. I'm just going to leave it like that for now. I'm taking this, I'm dissolving it in 500 milliliters of solution. Divide that by 500 mils, which is 0.5 liters. Multiply the whole thing by 2, you get 10, right? 10 over 82, and that's going to be your molarity inside of that solution. That now gets added to this. So now you have an equilibrium position, but now you have a new initial. Your new initial is this plus 10 over 82. And you have to recalculate the whole thing and figure out the new concentration and elevation of the acid based on Le Chatelier's principle. You guys see how that all works together? Common ion effect gives you this. You figure the rest out. You see how much is going to bounce back here. By doing, you're going to take this, get a new number, plug that into the Ka expression, 1.8 times 10 to the negative fifth equals 8.5 times 10 to the negative third plus 10 over 82, multiplied by 8.5 times 10 to the negative third, over x. X, because you're solving for this now. And you're going to see how much this elevates. Does that make sense? Good. That's how you do ice charts. And that's as complicated as an ice chart will get. You finish the equilibrium, find the common ion effect, do the molarity backwards, plug it back into the equation, set it equal to the original Ka, find the elevation, and it'll ask you how much does the pH change. But I've hardly seen that question even twice in my experience. You can do it, it just takes a while. It's a very long question. They'll probably give you a shortcut. They'll give you like incredibly easy numbers to work with. That's how you do ice charts. I'll make a quick note of something that I didn't do when I was studying for the MCAT because I really just brute forced my way through this. Solubility rules. If you can memorize these, more power to you. I can't. I definitely cannot. And that would be the end of the chapter and the end of our lesson today. Thank you guys so much for watching. Check the links in the description below to support me, and I'll see you next time for Acids and Bases. Take care.